Dear class, welcome to the second part of the control flow integrity lecture. Um, Let us start off from where we had stopped at the last lecture. I will briefly go over the instrumentation, and then we will talk about various assumptions of CFI, and then we will see how to relax some of these assumptions and how to make CFI even more robust with additional security tools that are enabled by CFI. All right. So, as we had discussed in the last class, our goal is to ensure that, or the goal of CFI is to ensure that the control flow of the program at runtime follows a statically determined control flow graph that is provided by a security analyst. So, in other words, the goal is the following: you want to build a binary instrumenting tool that will take the binary program and that will take the control flow graph provided by the security administrator and will insert instrumentation so that at runtime the binary program follows the control flow graph provided by the security analyst. All right, so what sort of properties do we want in the control flow graph? If we recall last time, we had essentially spoken about the property that we would like to enforce, which is that every call instruction, once if there is a direct call, of course you know the destination of the call. If there's an indirect call, such as this call 17R, again, this is not a real instruction in assembly code. This is an instruction that we have introduced. It's like pseudocode. We would like to understand, or this is the kind of instruction that we would like to enable. So call 17R is a very special kind of call instruction. This is what we are going to try to emulate or implement using x86 instrumentation. Call 17R performs an indirect jump based on the value that is stored in the register R. Now, the idea behind this call 17R is that you're going to check that at the destination, that is at the location as specified by R, when you actually go and change your instruction pointer over there, that the code actually contains a label 17, which matches what is present in the call. Okay, so this 17 is put over here as a result of this pre-analysis of this control flow graph, and the instrumentation will ensure that a label 17 is put at the destination and that the corresponding call instruction will perform a check and make sure that the label is indeed 17. Now, on the return path, of course, you want to make sure that the return goes back to the location where you came from. But we're going to be context insensitive in the first iteration of our of control flow integrity. So the returns are going to be marked with an annotation that says that you can return to any one of the locations from which this function can potentially be called. So for example, this less than function, it is called only from one location, and that we have determined using, let's say, pointer analysis. This return 23 specifies that you can only return here. Same thing for this greater than function, right? It's returning back to the same location where you had called it from. On contrast, this particular function sort is called from two locations. For the first one over here and the second one over here. And we would like to make sure that the return goes back to the location where you had started from. And essentially what this does is that the return makes sure that you are returning back to any one of the two locations. That's one of the things that CFI, at least in this first iteration, is going to do. You're going to return back to either this location or this location. All right. All right. So this is how the instrumentation is inserted. What you see on the slide is, on the left-hand side, you see the source, and on the right-hand side, you see the destination. Let's just assume that at the source, the instruction that we have is an indirect jump, where you're jumping from where you're using a jump to a particular destination that is calculated within this registered ECX. And let us just assume that the jump happens to go to this particular location where the destination happens to have this move instruction. All right. So we don't know the exact address of this move, this particular instruction. It's not provided over here, but we do see the opcode, right? It's 8B442404. All right. So the instruction that you're going to insert, remember, the main goal is to do the following: is to provide the equivalent of a label on the left hand side as well as on the right hand side. So the source must have this particular label and the destination must also have this label. So now what we're going to do is that when we have this jump ECX, this is the actual indirect jump. The indirect jump is going to be preceded by the instructions that emulate this label. So what we're doing is that the label is going to be the hexadecimal number 1234567 hexadecimal. So we are doing move EA 1234567 hexadecimal to EAX, incrementing it so that the register EAX has the value 1234567 then comparing it with the value at the destination. In fact, if you're going to jump to ECX, we are taking the value at ECX plus 4 bytes and comparing it. Why so? Why plus 4 bytes? Well, that becomes clear when you look at the destination side instrumentation, which is essentially saying you're going to put a prefetch NTA instruction. This is just an instruction that prefetches things into the cache. It does not have any other side effects. So that's the prefetch instruction, takes 4 bytes. That's why you have a plus 4. And the next instruction is just saying prefetch this value, right? So it's just going to prefetch this value into the cache. So when you execute this instruction, nothing really changes with respect to the program semantics. All it's doing is that it's prefetching something into the cache. So it's not really going to change the effect of the program. So this number over here is the 1234567 hex, and during normal course of execution, you expect that this jump value will actually go over here only after the label has been computed, right? So you can only go to the locations that have this corresponding label. Now you might have a number of questions, right? Which is, you've got this 1, 2, 3, 4, 5, 6, 7, 8. So why 1, 2, 3, 4, 5, 6, 7, 7 followed by an increment? So I will make that clear very shortly, right? It will become very clear once we talk about the CFI verifier. So the idea behind the CFI tool is the following. So let me just show you by drawing on a Jamboard. Just a second. All right. So I drew on the Jamboard and we will see what I have to show you. So all right. I hope this is visible, but the idea is that, as I was mentioning, there is a binary and a control flow graph that's provided by an analyst. You provide both through this box called a CFI instrumenter. The outcomes an instrumented binary of the form that I just showed you. But the key thing is that x86 is a very complex language, and an instrumenter, a CFI instrumenter, is also expected to be a rather complex entity. And so if we were to build our security of, or if the security of control flow integrity were to rely on the correctness of this binary, indirectly we are implying that the CFI instrumenter should also be correct, or that we have to trust the CFI instrumenter. If you have to trust the CFI instrumenter, then that essentially means you have to go and verify this extremely complex piece of software. Now that is beyond the realm of current technology, and so we are not going to attempt to verify the entire CFI instrumenter. Rather, we are going to take the instrumented binary and ensure that a few simple properties hold. The simple properties that will become clear in the next slide are going to be verified by the CFI verifier. And the CFI verifier is going to verify these properties by going over the instrumented binary, making a linear pass over the instrumented binary, making sure that these three simple properties that we are going to be asking for are actually satisfied by the binary. If they are indeed satisfied by the binary, then we can be sure that this instrumented binary is now going to satisfy control flow integrity when it's actually executed. So what have we done? What have we done here? The main thing that we have done is that we have changed the trusted computing base. Instead of the trusted computing base including the entire control flow integrity instrumentation tool, which is going to be rather complex because it has to deal with the entire complexity of the x86 instruction set, we're going to instead move our trust to a simple around less than 1000 line CFI verifier, because the job of the CFI verifier is going to be logically much simpler than the CFI instrumenter. And therefore we have been able to reduce the size of our trusted computing base. The size of our trusted computing base is just the size of the CFI verifier. Now let us go back to the slides and then see exactly what these assumptions are. All right, so in order to verify the CFI instrumentation, we have to make sure of the following properties: that whenever there are direct jump targets, so for example, if you have a call instruction that has a hard-coded destination address, then all you have to make sure when you get the control flow graph is that hard-coded as destination address of the call or a jump or any one of these instructions that does a non-local control transfer, that the target of that direct jump is in fact a valid target according to the control flow graph. So this is a very easy check. All you need to do is to go and search for all the call instructions, jump instructions, and all the non-local control transfer instructions that have direct targets as listed in the binary, and just go check that the target that is specified as part of that instruction in fact makes sense according to the control flow graph that the security analyst provided. That's property number one. That's an easy property to check. You can do it in a single linear pass, or at most 2 linear passes over the binary. The next property that you want to verify is that is regarding the IDs, right? You want to make sure that there is an ID which is this label. We place these labels, right? The 17 right at the entry point over here of less than, as well as greater than, as well as we place this label over here at the return point. So all we want to make sure is that an ID appears right after every entry point, and we want to make sure that every entry point that is legally permitted by this control flow graph that is provided by the security analyst has this ID. Okay. The next important property is that we want to make sure that this ID, which is nothing but a hexadecimal number, at the end of the day, this is an ID that you're providing in code. As you can see over here, the way we are doing instrumentation is that the ID is a hexadecimal value that is actually written down in the code. That's written down as a hexadecimal value in the code. So you want to make sure that this ID does not appear anywhere else in the binary by accident. So why do we want to make sure of this property? Well, the reason we want to make sure of this property is that this identifier, if it were to appear anywhere else in the code, if the same pattern 1, 2, 3, 4, 5, 6, 7, 8 were to appear anywhere else in the code, then in some sense what that does is that allows the attacker to treat that particular location potentially as a target of this particular jump. Right? So this jump over here is going to be allowed only if this byte is 1, 2, 3, 4, 5, 6, 7, 8. And now if you inadvertently allow this 1, 2, 3, 4, 5, 6, 7, 8 to appear somewhere else in the binary, then that particular location can potentially by the attacker be misused as a jump target of this indirect jump. So you want to avoid this 1, 2, 3, 4, 5, 6, 7, 8 from ever appearing anywhere else in the binary other than the valid destination addresses. Now that should give you the answer for why you actually produce 1, 2, 3, 4, 5, 6, 7, 7 in this binary rather than 1, 2, 3, 4, 5, 6, 7, 8 at the source destination at the instrumentation inserted at the source. The reason we did that is because you want to avoid even the existence of this 1, 2, 3, 4, 5, 6, 7, 8 at this source location, because you don't want this particular instruction over here to even by any chance be considered as a destination instruction for this jump. And so that is the reason why you actually you took the previous number and you computed this 1, 2, 3, 4, 5, 6, 7, 8 in memory and then jump to that location. Okay, so That is the second check. You want to make sure that there's an ID after every entry point and that the ID appears nowhere else in the binary except at the valid destination targets. Okay. And the third property you want to check is that the ID check happens before every control transfer instruction, and that each check respects the control flow graph. So before every indirect instruction, you want to make sure that there's an ID check of this sort, that the ID is actually being compared and checked, and that each check is actually respecting the CFG. So you're going to actually check for this equality, and if not, go to an error location. So that is what we have got. Those are the properties you want to check. So these three simple checks, as you can imagine, in fact, you can write down an algorithm. Given what I have described to you in simple terms, you can take each one of these three checks, and the way you implement these checks is by a simple linear walk over the binary and check instruction by instruction whether these rules are followed. Okay, and so if you're given a binary that is supposed to be adherent to CFI. So for example, if somebody gives you a binary, okay, and if somebody gives you the CFG, so in fact there should be one more arrow over here, and the missing arrow is the CFG should also be passed to the CFI verifier. If I'm given an instrumented binary and if I'm given a CFG, I can actually write a very, very simple CFI verifier that tells me just two answers. It gives me a Boolean answer saying yes, the instrumented binary is correct according to the CFI properties, and that all destinations in the instruction in the CFI instrumented binary are only those permitted by the CFG, or no, this is not good enough. In which case you can try to find another CFI instrumenter. Okay, so the CFI verifier's job is just to say yes or no, and if it's yes, you can just take that binary, you can trust the simple verifier, which is around 1,000 lines of code, and you can run it with the assurance now that this instrumented binary is going to satisfy the CFI property, which means that at runtime, this instrumented binary is going to follow the control flow graph. Okay, all right. Okay, so that's CFI. Now let's go back and revisit our assumptions and understand why these assumptions were made. If you were to think back to the original introduction of CFI, I had made some assumptions, which is that data memory is not executable, code memory is not writable. In fact, there's a third assumption, which will only make sense now that I have described the instrumentation, which is that it should be you should have unique IDs. Okay, in other words, every potential jump location or every potential return from a function should be grouped into equivalence classes and given a unique ID that does not appear anywhere else in the binary. And we saw the reason for it, right? We saw the reason for that because if it appears anywhere else in the binary, the attacker can potentially misuse that location as a potential target of a jump. All right, so the UNQ, or the unique IDs assumption, ensures that the CFI semantics are in fact preserved by ensuring that the IDs are unique at all the locations. We need NWC, or non-writable code, because remember, what we are doing is we are actually changing the code. We are actually going and modifying the code, inserting instrumentation, and the security of the entire technique is relying on this instrumentation to be sound, right? So you don't want the instrumentation that was so painfully inserted and actually verified by the CFI verifier to ever change. So that is what we are doing over here. We are making sure that that the code is not writable. Okay, so the attacker cannot override the CFI check, and this is not true if the code is dynamically loaded or generated. Okay, so if you have got dynamically generated code, for example, just-in-time interpreters, or if you have got dynamically loaded libraries, you want to make sure that every dynamically loaded library is also instrumented with CFI, and that if you're generating any code, then you want to make sure that the code you're generating also has corresponding instrumentation of this sort, or you need to be able to trust that code. So that's the non-writable code assumption. And the third assumption is that of non-executable data, which you want because you can cause the execution of data labeled with the expected ID, right? So you don't want to do that. You can always inject code into the program, and that's going to have the expected with you can inject the code into the program. You can call it data, and you can also insert the corresponding ID. For example, in a stack based buffer overflow, you can insert both the ID as well as any injected code you want to execute, and then transfer control over to that, and then that will just still satisfy the CFI assumption, and the attack will succeed. So in order to avoid those kinds of attacks, we are going to make the assumption of non-executable data. Of course, U and Q or unique IDs is verified for you by the CFI verifier over here, right? So we checked it over here that that the IDs checks we performed in the CFI verifier, so that's actually being performed. These two, NWC as well as NXD, are going to be provided to you by the operating system, where the operating system, we can set the page table permission bits so that we have non-writable code as well as non-executable data. All right. So that is that is the reason why we need these assumptions, and hopefully this should also allow you to reason about the security of CFI. Now, all right. So let's look at the security guarantees that CFI provides, right? So CFI is very clear in the sense that it is a defense that protects against attacks based on illegitimate control flow transfer. In other words, any attacks that modify control data in the program and cause it to move to any locations in the program that are not authorized by the control flow graph, those kind of attacks you can catch. Okay, so you can catch things like stack-based buffer overflows. You can catch things like return to libc exploits, because those also work by modifying the return address. You can also protect against pointer subterfuge, which are attacks that override pointers, for example, function pointers, and make them point to attacker created locations. You can defend against all of these kinds of attacks. You have to be clear about what CFI does not protect you against. So CFI does not protect you against any database attacks that do not violate the original program's control flow graph. So for example, if you have a local data variable whose value you can modify, and then perform an attack based on just modifying that local variable's value, then those are not possible to defend using CFI. Okay, so those are called data only attacks, and those cannot be defended using CFI. You cannot prevent attacks whereby an attack injects incorrect arguments to, for example, system calls. So it should be clear that the system call is actually allowed from the location, but the argument is the only thing that is available for the attacker to modify. And if the attacker can modify the argument and still proceed with the system call, that is not an attack that can be potentially defended against by CFI. You cannot change, for example, you cannot protect against, for example, attacks that goes and changes file names, right, when the program is reading from disk. So these are, for example, parameters that appear in the configuration files of the program. You cannot protect against that. And of course, if your program itself has incorrect or buggy logic, you cannot protect against that, because you're given the control flow graph, and that's the only thing you're enforcing. All right, so very quickly, an evaluation of CFI, and this is straight from the paper, and these numbers are around 15 years old, so I would not place too much value on them. This is just to give you an indication of the ballpark estimates. If you're interested in learning more about how CFI is applied in the real world, there are links for that. So there is GCC and LLVM implementation of control flow integrity. Let me just give you the reference, and you can go and look it up. Right. So you can see that both LLVM as well as GCC, which are the most popular compilers that are out there today, actually have an implementation of control flow integrity. And this particular paper actually talks about the implementation of control flow integrity in GCC and LLVM. As you can see, the number of contributors from Google have actually contributed to this implementation. So you can go and download it and try CFI yourself. The description of the techniques of what has actually been implemented, they are an advanced version of what you're studying now in this particular lecture, but essentially that has been implemented in GCC and LLVM. You're welcome to actually go and play around with GCC and LLVM, and the overheads have been substantially reduced from the numbers that I'm showing you over here. So on the x-axis over here, you have various benchmarks from the spec benchmark suite. Spec 2000, it's a standard benchmark suite that was originally created for benchmarking program performance. And what you can see over here is on the y-axis are the control flow integrity enforcement overheads. That is the extra overhead that is introduced by the additional instrumentation that you inserted. You want to see how much it takes, and on average you can see across the spec benchmark suite it's around it lies between around 10 to 20%. Around 15% is the overhead. This is still pretty large, right? I mean, overheads of even a few percent, 5% are typically unacceptable to real world developers, but that's why a CFI has been optimized, and it's been brought down to the extent that now you can actually use it. And it's many cases people view the additional overhead as being worth the effort, right? I mean, you want a secure program rather than something that is going to get hacked, and so it's worth it to pay a little bit more in terms of performance and obtain security instead. All right, so in terms of evaluation, your control flow graph and the CFI instrumentation itself, for around the spec benchmarks takes around 10 seconds, and the binary size also increases. So this has direct implications in terms of the cache behavior, memory footprint of the application, and it takes around 8%. And you can see that the relative execution overhead, the worst case for a benchmark called Crafty, it was 45%, and GCC is less than 10%. Okay. And in the paper, if you were to go and look, there are a number of security related experiments that really talk about how CFI protects against specific attacks. So for example, if you were to take the format string attack that we spoke about in the previous lecture or 2 lectures ago, that is a particular attack where this %n parameter was used to go ahead and overwrite an arbitrary memory location in the program's memory with an arbitrary value. Okay. Now, you cannot prevent that even if you have CFI instrumentation. But what you can prevent is that if that %n was targeting a control data location, and if that %n was used to override that control data location with a particular value, so for example, the address of some injected code, then that attack will no longer work because the label check will fail. Okay, so you can protect against those kind of attacks. Now, of course, if the %n goes and changes the value of a local variable, as mentioned in this particular slide, you cannot defend against that attack using CFI because it cannot protect against data-only attacks. Now, contrast this with Softbound. So in Softbound, you cannot protect against printf format string vulnerabilities because it only checks for buffer bound. It only checks for bounce checks when you're writing into a buffer or writing into memory. It only checks for bounds. And when you did the printf format string attack, you did not violate any bounds. You just wrote to an arbitrary memory location an arbitrary value. You did not violate any buffer bounds when you did so. So that is perfectly within the bounds of or within the rules of Softbound, but CFI can still catch that attack provided that the location that's overwritten is a control data location, and that it's overwritten with a value that's not permitted by the control flow graph. Now also note from this particular slide that Softbound can actually protect against certain data-only attacks. So Softbound will actually protect you from corrupting or overwriting the local variables that are there in a particular function. So you can prevent the overwrites of those integer variables or any other variables that are adjoining the buffer, because it is going to throw an exception the second that you write past the end of the buffer. So in contrast, CFI will not protect you against that, but it will make sure that even if you override all of that, that the control transfer that does happen eventually is actually in accordance with the control flow graph. Okay, so that is what That's how you compare CFI and Softbound in terms of the power, right? So you saw one example where Softbound can prevent certain attacks that CFI cannot, and in some other cases, CFI is capable of defending against some attacks that Softbound was not really capable of defending you against. Okay, so complementary techniques in terms of what they're able to provide. Completely different bases. In the case of Softbound, of course, we needed access to the source code of the program. In the case of CFI, you're able to do all of this without access to the source code by direct binary instrumentation. And in terms of the amount of trusted code that you need, is also much smaller in the case of CFI, because you're only trusting the binary verifier. You're not really you don't have to trust anything else. Okay. All right. So let us now move on from CFI and let's look at some additional security mechanisms that CFI can enable. That is, that makes the program much more secure, because now CFI is going to protect the security of these additional mechanisms. Okay. So the first thing that we are going to talk about is SFI, or software fault isolation. So SFI is software fault isolation. It's a technique that was introduced in 1993, and I will tell you about it. But what CFI does is that it implies non-circumventable sandboxing. That is, safety checks inserted by the instrumentation before a particular instruction will always be executed before reaching X. Okay. So if you're inserting any security checks before a particular instruction in the program, then CFI, or control flow integrity, make sure that the target of any jump cannot directly reach that instruction. It'll actually go through the instrumentation. Okay. So an important side benefit, an important property that CFI actually offers is that of non-circumventable sandboxing. Okay. And what is SFI? So SFI is a software-based fault isolation technique that I will tell you about in just a second. Let me open the original source of software-based fault isolation, and we can look at the at what it provides. And let me just give me a moment here. All right. So let me tell you about software-based fault isolation. So software-based fault isolation is a particular security technique that is used for sandboxing. Okay, so software-based fault isolation, the overall goal of software-based fault isolation is to make sure that you create lightweight protection domains within your logical address space of the program's memory. Okay, so what you want to create are these fault domains, so that any fault that happens, or any bug that happens, or any mistake that happens during the execution of the program is confined to that one particular domain. It does not escape that domain. Okay, so in particular, you want to make sure that there is a particular data region where the runtime data is stored. So you don't want to see, this is very similar to the WX or X policy, where you want to make sure that, yeah, there is a particular portion of the program where data is stored and another portion where code is stored, and that there is no mixture. You can enforce this using SFI. You don't need operating system level techniques. So for example, using SFI, you can ensure that there's a data region where runtime data is stored, and just to ensure that the data region is demarcated, let's just call that DB and DL as the limits of this data region. So DB is the address from where the data region starts. DL is the end of that data region. Now let's just assume that we have likewise a code region with a code begin and a code end, right? That's the code region, and you want to make sure that there is a set of safe external code addresses outside of this fault domain. Okay, so whenever you move to this safe location, so this we will see this concept of safe locations and safe code when we talk about Intel APK in about 2 or 3 lectures from now. But these are, for example, instrumentation code that you insert to make sure that the program is doing some additional checking, and you want to make sure that this code, nobody can jump to this code. But let's for a second put this on the side and let's focus on DBDL and CBCL. Okay, so you want to make sure, so CFI allows you to ensure that if you have a code region, that any control transfers happen, let's say, only to within the code, and from this code region, if you're doing any control transfer, it's okay to go to the secure region SE that is shown over here, and that if the code performs and it reads or writes, that it's only going to this data region, that it's not going anywhere else. Okay, so SFI allows you to ensure all of this using binary instrumentation. So how would you do this? It's very easy, right? Just imagine how you will enforce a policy, for example, that any reads or writes from this code region go only to this data region. Before any load or store instruction, you will insert some code in this program to make sure that the address of the read is greater than db and less than dl, or the address of the corresponding write is less than this db and greater than dl. At runtime, you'll make sure that this check is satisfied, and you will do this by actually inserting the corresponding instrumentation, this check, this less than greater than check, in the code region. Okay, so you want to make sure, in order for the CFI, for the software based fault isolation technique to succeed, you want to make sure that that instrumentation is actually executed. If ever there can be a situation in this program where you can jump into this code region and bypass those instrumentation, then of course, the read or write, because you have not performed the check, you can go anywhere. Right? If you want to ensure that the reads or writes only go to this data region, you have to make sure that before the read and the write, those checks are in fact performed. So how do you do this using CFI? How do you make software-based fault isolation stronger using control flow integrity? Well, what you do is that you make sure that if there are any jumps in this program, indirect jumps, that they actually go to the first instruction of the corresponding instrumentation, and make sure that the instrumentation instructions are executed before the read and the write instructions actually happen. Okay, so SFI is inserting these dynamic checks of the form that I just told you to ensure that the target memory accesses lie within a certain range. So for example, that the target memory accesses of this read and write are between the DB and the DL and within this data region. And what you're ensuring is that using CFI, you're ensuring that these checks are non-circumventable. And how do you make sure of that? Well, you make sure by ensuring that any jumps in the program that go to these read or write instructions that are performing these reads and writes are in fact not directly going to the read or write instruction, but to the instrumentation before the read or the write, so that the corresponding checks are performed and the DB-DL range is enforced whenever you're reading or whenever you're writing. Okay, so that's how you're able to enforce software fault isolation in a much robust way using control flow integrity. All right. So the paper also talks about a much more generalized version of SFI called software mandatory access control. And I'm going to let you read this from the paper itself. It's a rather straightforward generalization of SFI, where what you're doing is that instead of performing the same check everywhere in the program, you're actually performing different kinds of checks at different locations in the program. You still have the same guarantee that, so SMAC is just a new security defense. It has nothing to do with control flow integrity, but control flow integrity can make sure that SMAC is much more powerful and it's much more robust, because you can make sure that the checks introduced by SMAC are non-circumventable. Okay, using exactly the same technique that I spoke about just now. Okay, so here, right, I'm going to show you an example of CFI plus SMAC, and here it is, right? So you've got a call instruction. The call is going to some location as determined by this register EAX. It's a call via function pointer. What I've shown you over here are the checks that you're inserting into the program. So for a second, let's just forget the AND instruction over here. That's the new check that you're introducing for SMAC. But the remaining checks you're familiar with, right? This compare EAX plus 4, 1, 2, 3, 4, 5, 6, 7, 8. This is the one that's actually talking about comparing the opcodes. This is the standard, CFI instrumentation. Okay, and this prefetch NTA is the label that is to be checked upon the return from this function. Remember, all the potential targets of a potential destination of a control transfer have to be instrumented. And while I showed you the corresponding branch target, I didn't show you the returns. This is how you instrument for the returns. Now, this call instruction is now preceded by these instructions. This is the new instruction that's added. What is it doing? It's actually a mask instruction. You're putting an AND, you're masking the AND together with this hexadecimal value, where you really don't care about the lower bits, but the top bit you want to make sure that in fact the top 8 bits you care about, you're enforcing a particular pattern, right? This pattern over here is in fact 0 1 0 0 0 0 0, right? You're ensuring that this particular code that you're jumping to is in code memory. Okay, so if assuming that that is the location, that's the range, these 8 bytes over here should be constant for the code region. Everything else you can vary, right? The code region. So anything that is in 0 1 0 0, and then doesn't matter what address, that's supposed to be code. If you assume that this is the code region, then what you're doing over here is a very simple check to make sure that whenever you're jumping via this call instruction, that you're only jumping within the code segment. Okay, so again, you're doing a further check over here to make sure that you're only going to be jumping to valid locations, but this very first check over here, make sure that you're jumping only within the code region. Okay, so now given SMAC and given this particular kind of check, right, you can actually get rid of the non-executable data assumption of CFI, in the sense that this non-executable data assumption, which you enforce using the page table bits and making the pages, data pages non-executable, you can get rid of that assumption, because the SMAC or the SFI instrumentation that you inserted into the program is actually enforcing that for you. So now with SMAC, so you took CFI. Now imagine how we built things. We made certain assumptions. We built CFI. We argued about the security of CFI. We are using CFI to build a much more powerful security mechanism. And we find that this much more security mechanism actually allows us to relax some of the assumptions of CFI, right? So this might seem like circular logic to you, right? I made some assumptions here. I built a more powerful defense, and this defense is now allowing me to weaken some of the assumptions of CFI. Doesn't that compromise the entire technique? So the paper, in fact, not this paper, but a follow-up paper had a full formal proof showing that, in fact, CFI is robust and that you can actually prove its security. Now that paper, even though the slides over here talk about that proof and so on, that paper is not assigned reading for you, so you can skip that portion of these slides. Okay, but it's kind of it's unique over here, right? I mean, in the sense that we are talking about a particular assumption that allowed us to build CFI, which we are now relaxing because we have CFI giving us protection of another defense mechanism that we just built. So it's very, very unique in that sense. All right, so there's one more called generalization of SMAC called inline reference monitors, or IRMs. I'm going to skip that. It's there in the paper. It's fairly straightforward. So what's an IRM? An IRM is just a security property that's expressed as an automaton. So you want to make sure that the program is in particular states and that you can transition these states only at certain locations, and will allow you to go and read this directly from the paper. But I do want to talk about one more defense that is strengthened by CFI, and that is CFI with context sensitivity. Okay, so let's go back to CFI, and at least the slide that talked about the requirements of CFI. So in CFI over here, we spoke about the returns from here going back to this location, and that's okay, because this less than and the greater than, at least this program, they were only called from this location. But this sort was called from two locations. It's called from here and it's called from here. Okay, and the return can go to either this or this, right? That's how we inserted the labels, right? By doing a simple analysis, we found that this sort is called from here. It's also called from here. So the corresponding return from the sort can either come here or here. It cannot go anywhere else. That's what CFI will give you. But it still is context insensitive, because this sort, if an attacker so has the power, he can make the sort that goes from the first location go back to the second return location, or a sort that's called from the second location go back to the first return location. And you want to strengthen that also, right? How do you make sure that that is not possible? So the way that that is possible is that in addition to these label checks, you're also going to check a shadow stack. You're going to maintain a shadow stack in protected memory that you can protect, let's say using SMAC or SFI, a data location where you store the return addresses. It is a shadow stack, right? So instead of the actual program stack, you're keeping another stack in protected memory, kind of like the location where you stored your canaries for the stack canary based defense. And you're going to make sure that whenever you return, not only does the label match, it also goes and matches the exact address. So if you were called from here, you can only return over here. And if you're called from here, you can only return over here. Okay. So the way you implement that particular defense is using the shadow stack. So a function f, if it is called from a particular location A and it's again then called from B, what is a valid return destination for this return? As we just saw, CFI uses the same tag for both call sites. Okay, so this allowed f to return to B after being called from A. In other words, it allowed sort to return to the second location after being called from the first location, or vice versa. Okay, so one solution, of course, is to duplicate the code, right? Even have one copy of the code for every unique invocation. That's called inlining, and we saw that it has its own limitations. We went over that last program in the last lecture. Okay, so instead, a better solution is to use a shadow stack. You place this stack in a SMAC protected memory region, so it's not writable from any other location except from this instrumentation. Right? Only the SMAC instrumentation of the call and the return can modify the stack by pushing and popping values, and you statically verify that this instrumentation code is correct. And the shadow call stack keeps a stack of return values that you can return to. Okay, so this way you can enforce context sensitivity. Okay, so what I want you to see over here is how with CFI we have built one technique over the other, right? So with CFI, we were able to provide some basic security. We use that to build software fault isolation. We generalize that to SMAC. And using SMAC, we were even able to relax the assumption of non-executable data. And using SMAC, we were able to implement a shadow call stack. So we have built a tower of defenses in some sense that allows us to protect the program during runtime, right? So these are all applications of CFI that allow more and more stronger and stronger security. Okay, so that concludes our discussion of CFI. We are not going to be doing the formal study, as I said, right? It's there. I can give you a pointer to this paper if you're interested, but the paper that is linked from the class web page does not consider the formal study, so we will not be doing that as well. So that is it for CFI, and everything up to and including control flow integrity is going to be the portion for your midterm exam. There is going to be no taint analysis. Taint analysis will be after the midterm. So this is the last lecture that is relevant for your midterm exam. Okay, so I am not going to be present during the class hours on Monday, November 2nd. So that is why I've pre-recorded these lectures. You can always, you're welcome to post any questions that you have regarding this lecture on Teams. And when I can, I will go there, I will check for your questions, and I will actually go and answer them. All right. So thank you very much for your patience. Let me pause the recording.